Welcome back, fellow humans. I'm Jason. Today I'd like to tackle a persistent myth you may have heard that's baffled and misled many people for over a century, and that is an atom really 99% empty space? So you probably heard this or been taught that the nucleus of an atom is incredibly tiny and that the electrons whirl around the nucleus at great distances, and so it follows that the atom is mostly empty space. But is that true? Buckle up and throw your common sense out the window, because today we're about to debunk this misconception and dive into the really weird world of quantum mechanics. So you may have seen the movie Honey, I Shrunk the Kids, right? The premise of that movie is that the atom is mostly completely empty space in between the nucleus and the electrons, and so the invention there is able to shrink all of the atoms by compressing all of that empty space, and so everybody gets shrunk down. That's the whole point of the movie. And so we've all heard it before. Atoms are 99.9999% empty space. But what if I told you that that's not exactly true, depending on how you interpret things? The idea of atoms being mostly empty space only holds water if you kind of think of electrons as tiny, hard little balls going around like a solar system or planets orbiting the sun. But we know that electrons don't behave like that at all. In reality, electrons are quantum objects that defy our classical understanding of particles. And I'll just tell you right now, you'll do well to just take that thought of electrons being planets, like balls that just go around, and just throw it out the window. I mean, it has its uses. It does help us visualize in some cases what's happening, but electrons are very far away in reality from behaving like little hard balls like that. It's a good concept to teach like a fourth grader, but it isn't really how electrons behave at all when we do actual experiments with electrons. So what's actually the real story here? Let's start with the basics, all right? So no one's left behind. Electrons are not little balls. Just throw it out the window. They're what we call quantum objects that exhibit both particle-like and also wave-like properties. So when electrons are stable inside of an atom, they behave almost entirely as waves. So picture this. Instead of a single point, which is kind of what you're taught when you're young, an electron spreads out as a three-dimensional cloud-like quantum wave, filling the entire atom. Now, these wave-like states of electrons are known as orbitals, and here's the kicker. There's no empty space in an atom because these orbitals fill the entire volume of the atom. The electron doesn't simply occupy a spot inside of the orbital. What's actually happening is the electron is the orbital. And so it's a fundamental principle of quantum mechanics that electrons are not particles orbiting a nucleus like inside of some volume. They're instead spread out as waves occupying the whole area around the atom. It's sort of like a cloud. Now that's actually so important that I want to say it again because it's the critical thing to understand here. You're taught that the nucleus is in the middle and there are these balls called electrons that go around, and that's how they're drawn in books. But we know from quantum mechanics and from experiments that it's not like that. They are not little balls that whiz around. Inside of an atom, an electron is expressed as a wave function. It has a wave-like character. And a wave is something that waves up and down. But in the space around an atom, it's not an up and down wave. It's a three-dimensional wave that fills the entire volume. What does that wave represent? I'll draw some pictures in a second, but the wave nature of the electron it represents the probability, really it's a probability density, but the probability of where the electron will be if we were to measure its location. So when we measure the location with some sort of, not your eyeballs or your brain, but some kind of like an instrument that would, detect where it is, then the wave function is said to collapse, and then we measure the position of the electron in a certain location. And that is why we think of electrons as existing as little dots. But really, when we're not measuring them, meaning we're not interacting with them with some measurement apparatus, they spread out into waves. And we know that because of experiments with interference, and we can see the electron waves interfering with each other, just like water waves might interfere with each other on a beach or in a wave tank. So around an atom, what's really going on is the electrons don't exist as balls that are inside of some volume. That gives rise to the idea that it's mostly empty space. Reality, they spread out into a wave-like nature that exists in the entire sphere of influence of the atom. So it's not really empty space, it's just a completely different construct that we don't have everyday experience with. That's why we say things like, it's a quantum object, because we don't have everyday experience with things filling up and occupying multiple spaces at one time, which is really the closest analogy to what a quantum object actually does, where the wave function expresses the probability of where it'll be. If we were to measure it 1,000 times, we would see 1,000 different locations and we would get an idea of where it spends quote unquote most of its time. But it's not a ball whizzing around like that. It literally exists in all of those places at once, but in the form of a wave that spreads out in three-dimensional space. Now, I'd like to go a little bit deeper, and I am going to draw some pictures in a second that'll hopefully nail it down for us here. But I'd like to go a little bit deeper. In the early days of early quantum mechanics, before quantum mechanics was really invented, right? We really did think of the nucleus being a hard sphere and these hard balls called electrons going around, right? Just like planets in a solar system. That was the model, right? But we know from physics that when an object orbits, then it's accelerating. It's changing direction all the time, and that's an acceleration. And we also know that when something accelerates, then it is going to radiate energy away. We know that from Maxwell's equations of electrodynamics. When any kind of electron or charged particle accelerates, like in an antenna, that's what's happening. The electrons are going up and down and accelerating, and they're radiating waves out as a result of that. So in a nucleus or in an atom, the electrons are going around and they're accelerating as they go around, right? The change of direction is called an acceleration, so they should radiate energy, and so the electrons should lose energy for every atom in existence. That was the prevailing idea. And so if it loses energy, that electron should spiral in and collide with the nucleus, and the atom is not a stable thing. But we obviously see atoms everywhere, so it doesn't behave like that. It was a major, major disconnect in the early days of quantum mechanics. How can atoms be stable if these electrons are going around losing energy and they collide into the nucleus immediately, right? How can it be stable? So then a new theory was put forward, that maybe there are certain orbits where the electron doesn't lose energy. It's kind of an invention. You have to take a leap of faith. Maybe there are certain special orbits around an atom where the electron does not lose energy, right? And that was the prevailing theory for a while. But then, as we did experiments with electrons and figured out that they actually exist and behave like waves that can interfere with one another, like water waves do, then the idea started to crop up, maybe all particles of matter have a wavelength. And this is actually true. Just like photons have a wavelength, we actually now know that electrons have a wavelength. That's how electron microscopes work. And that's why we can see things smaller than visible light with an electron microscope. All right, so electrons can have a wavelength, protons can have a wavelength. All bits of matter have what's called a de Broglie wavelength, and they actually can interfere just like water waves can. So then the new sort of picture started to evolve. Instead of a nucleus, and instead of a hard ball called an electron going around like a solar system, maybe the distance from the nucleus is just such that the electron isn't whirling around like this. Maybe its wave-like character is waving and able to connect back in on itself in a special orbit at a certain radius away. And that's why it's stable, and that's why it doesn't lose energy. So you can kind of think of the orbital radius, the stable orbit of an electron, not losing energy. It's not losing energy because it's not a ball that's whirling around at all. It's a stable wave that connects back. The head of the wave connects back to the tail of the wave. And so it's a stable place where the electron can do its wiggling, and the front of it connects with the back of it and form a stable wave. If you think of a piece of string waving and then connecting back on itself, then it would form a stable configuration where it can do the oscillation and the waving. If it were too close to the nucleus, then it wouldn't close on itself and it wouldn't be a stable wave. And so electrons don't really exist with a high probability too close to the nucleus, for instance. I'll draw a picture, but that is the crux and the core of the idea here. I do want to be careful to point out that I'm doing a lot of very good simplification here and making it simpler. I want to make sure you understand that when I say it's a wave, it's not just a regular wave like at the beach. It's a wave that's represented by a complex number, a complex amplitude, and a complex phase. When you get into the math of waves, you'll learn that there's an amplitude, how high the wave gets, and there's a phase, how shifted are the peaks and the troughs relative to whatever you're measuring it relative to. But in quantum mechanics, all the waves have complex numbers. So in algebra, when you learned about imaginary number I, and you thought, well, this is completely useless, I'll never use this, the entire branch of science known as quantum mechanics relies on complex numbers to represent anything. And if you don't think that that has its uses, just remember that the transistor, all memory, all computer screens, anything to do with modern semiconductors, any computer chips, they all are possible because we understand quantum mechanics. If we don't understand quantum mechanics, we cannot make a transistor, which is what powers everything in the modern world. So complex numbers, imaginary numbers, very, very important. So it's important for you to understand that the electron forms this probability cloud in the vicinity of an atom. And it's not that an electron is something that exists like inside of this electron orbital that you learned about in chemistry class. It's that the electron itself is the orbital, and that's what I'm emphasizing with my voice. When you look at what the wave function of the electron is, it's not representing an envelope inside of which an electron might be. It is saying that the electron is the wave that extends in that space. So it's not really proper to say that an atom is mostly empty space, because an electron is like whirling around and it's only occupying a small part of this envelope. It's not proper to say that. It's more proper to say that the thing that we call an electron is something that is a complex wave that extends throughout space, and it is basically in that entire space all the time. When we measure the electron, sometimes we'll measure it here. Sometimes if we measure it again, we'll measure it over here and over here. And if we measure it 10,000 times, we will see that it is more likely to exist in a certain radius away from the atom. Sometimes a little closer, sometimes a little farther away. But if we do it 1,000 times, we'll see that there's a most likely distance that the electron likes to exist at. But that doesn't mean that it's like bouncing around and inside of that envelope. It just means that the wave function collapses to that location when we measure it. When we're not measuring it, it's more proper to say that the electron is a smeared out probability cloud that exists in space around the nucleus. I'd like to dig a little bit deeper into the concept of orbitals, which is something you learn about in chemistry class. So an orbital is just a representation of the regions around the nucleus of an atom where an electron is most likely to be found when we're measuring it. And they have all different shapes. You learn about them in chemistry and physics. The simplest shape is a spherical region around the nucleus, right? That's called an s orbital, S for spherical. But there are more complicated shapes. You have the dumbbell shapes that kind of have a lobe up above and down below the nucleus, and you have those dumbbells oriented along different axes, up and down, sideways, and so on. And that would mean the electrons would be more likely to be found inside of those dumbbell envelopes when we do measure them. But there's actually more complex shapes. When you go up and up in energy, you'll see that these wave functions around a nucleus can have very complex and beautiful shapes. And just remember that they're waves in 3 dimensions, but they're also waves that have complex amplitude. So it's not exactly something that we can easily visualize. We can kind of draw graphs, but it's hard for us to visualize complex numbers as an amplitude of a wave, because complex numbers have a real part and an imaginary part, so it's hard for us to visualize, but we can graph the real part, we can graph the imaginary part to sort of visualize what they look like. So the wave nature of the electron is a well-established cornerstone of modern physics and chemistry. It's not just some weird, quirky idea, but it's a crucial aspect of how atoms interact, how they form bonds with each other, which is all of chemistry, how they create the diverse matter that we see in the universe. And this wave behavior has been confirmed through countless experiments and forms the foundation of quantum mechanics and modern chemistry. So what I'd like to do first is draw a little picture to give you kind of a cartoon in your mind of how an electron can exist as a wave around an atom instead of this little ball that flies around. All right. So the typical idea that we have in our mind is that, let's talk about hydrogen, for instance. There's a single proton in the nucleus, right? We know there's quarks inside of there, but that's how we represent it. And then you're taught that there's a single electron here, put a little E right there. and it orbits out here at some distance away in some kind of three-dimensional way. But that's typically what you learn, when you're a young person. All right, well, another picture in your mind, which is again just a cartoon, is not correct, is instead of thinking about it as a ball that does this, think about this electron having some sort of wavelength associated with it. And the wavelength will depend on certain variables, but has some sort of wavelength, wave character to it. So instead of thinking about it as a ball, you can think of the electron existing as a wave that is around the atom like this, or around the nucleus, and it closes in. I can't draw it perfectly well, but it closes in on itself. Now, I have not done a good job because I've made this one bigger than this one. It's really hard to make it perfect, but the idea would be like a constant peak and trough and peak and trough and peak and trough and peak and trough, and it would close back in on itself. So at this certain radius, the electron is able to have a closed wave where the head connects back to the tail. And you can imagine like a piece of string, if you put a piece of string in a circle, but then imagine it oscillating like this, but with peaks and troughs that go in and out, but not just as a flat circle, but as some three-dimensional wave that's somehow pulsating and vibrating. It's very difficult to visualize because we're just not good at visualizing three-dimensional or four-dimensional things like that. But that is one picture to have in your mind. If the electron were farther away, then this wave has a harder time closing in on itself. If it were closer, it would have a harder time closing in on itself, so it's more stable here. Now, as we give more energy to the electron, right, more energy, then it will get, quote unquote, farther away from the nucleus, and that means that there'll be more crests and troughs as it goes all the way around that farther radius. And that's why as the electron gets higher and higher energies, you can think of it, instead of a ball whizzing around farther away, you think of a wave with more wiggles, so to speak, as it comes back and connects in on itself. Again, it's not perfect, it's just an analogy, a picture, but it gives you some kind of idea. All right, now what I want to do now is I want to talk to you a little bit before we go on and continue about the wave function itself. This is not a class in quantum mechanics, but I want to share with you something because I think everybody can understand it. Everybody can, even if you don't know or care anything about algebra or calculus or anything like that. So the electron, instead of a ball like this, it's represented by a wave function. This is the letter called psi, the Greek letter psi. And we put a little 1s here. In chemistry, you learn about the s orbitals. The 1 means it's the first energy level, the lowest energy level. And this means it's a function of r, right? It means as you get farther away, r has how far away you are from the nucleus, right? You can just think of this as r right here, right? And the farther away you are, then it's going to have some probability. This is representing the probability of the electron. And here's what you get in all of its glory. 1 over the square root of pi, and then there's something called a naught, which I'll tell you about in a second, to the 3/2, e to the minus r over a naught. Okay, pi is the regular old pi you learned about in algebra, 3.14, and goes on and on forever, right? A naught is just a number. It's not a variable. It's called the Bohr radius. I want you to hold that in your mind. I'll explain what the Bohr radius is in a second. But basically, it's that lowest radius where the electron likes to hang out. The first stable radius, as I've drawn on the board over here. You can think of it as the radius from here to where the electron's most likely to be found. And that's, shows up as a variable. So we just call it a naught, or as a constant. We just call it a naught. So in quantum mechanics, to figure out the actual probability of where the thing is going to be, what you do is you square the wave function. And then you, not only do you square it, but after you square it, you use calculus to what we call integrate or add up all the little contributions of the square of the wave function, and that tells you the actual probability. So if you want to know, because this is what's called a probability density. It's telling you the fractional probability everywhere in the cloud. If you want to figure out the total probability of the electron being between radius 1.1 and 1.2, then you have to integrate a shell all the way around. You have to integrate that density up. Just like we add up density in like physics or whatever, and we get the mass of an object. We have to add up the little contributions of density over the volume. We have to add up the contributions of this probability density to get the actual probability of where the electron is going to be, right? But before we add it up, we have to actually square it. So what we do is we define something called 1s r, take the magnitude, which means how big it is, and we square it. all right? So when you do the squaring operation over here, the square of 1 is 1, the square of the square root of pi is just pi, and when you square this, the square and the 2 here will cancel, and so you'll have a naught to the third power, right? And when you square this, it works out to e to the minus 2r over a naught. But what I really want to do is I want you to recognize that everything in front of the e is just a constant. It's a number. This is a number, this is a number, and this is a Bohr radius. It's just called a number, and it's cubed. So everything out in front is a constant. So this is a constant. And then everything in here, except for the radius, is also a constant. That's a constant, that's a constant, and that's a constant. So really what you have is this whole thing is proportional to a constant multiplied by e to the minus constant r, multiplied by r, because this is a constant, the 1 over a naught is a constant. So basically what I'm trying to get you to realize is that even though the formula looks really complex, just throw away the constants. They're just numbers, okay? And focus on the shape of what this looks like. When you square it like this, then what you get is just from math class, like from algebra from a long time ago, it looks like e to the minus r. If you ignore the constant and say, okay, that's just a number, and you ignore this constant, okay, that's just a number, then really it looks like it's approximately proportional to e to the minus r, which is 1 over e to the r. That's what a negative exponent is. You drop it downstairs and you make it positive. So what I'm trying to say is that the wave function of an electron around a hydrogen atom looks ugly. But when you square it to try to start calculating the probability of where the electron will be, what you get is just a constant times e to the minus r times a constant. So if you just ignore the constants and say, what does it really depend on? Then it's 1 over e to the power of r. Now, what does that look like from, like algebra from a long time ago? When you graph this, right? When you graph this, 1 over e to the r looks like a curve that just drops off like this. So what happens is the radius gets smaller than the probability of finding the electron, or not the total probability, but the fractional probability seems to get higher as we get close to the nucleus, because the nucleus is here. But then as we get farther away, the probability drops off, and it never approaches 0, but it gets smaller and smaller and smaller. So what you do, if you really want to figure out where the electron is going to be, you take this square of the wave function, which is all this stuff here, and you have to, what we call in calculus, integrate it, which means you add up all the contributions around a shell around the nucleus. And so what you get when you do that is, what you get is the actual probability of finding the electron. So probability of finding the electron. And what you find out is it looks something like this. It goes up to some maximum peak, and then it drops off and gets kind of like close to the x-axis like this. And this distance right here, where the peak of this thing is called a naught. That's called the Bohr radius. So what happens is, this is the probability of finding the electron in a hydrogen atom. What you find out is there is some maximum probability called a naught. Notice that it runs around our equations. That's why they label it, because it's called the Bohr radius and it's special. And the electron is most likely to be found here. If you measure the position of the electron in the atom for the lowest energy level, most of the time you're going to find the electron, once you measure it, hanging out somewhere around the Bohr radius. The maximum most likely probability is here. But there is a chance that it's closer to the nucleus, but notice how the probability falls off and approaches 0. But actually, interestingly, it doesn't actually ever get to 0. So there is a small chance the electron can be in the nucleus, which is weird. Very, very small chance, but it's there. But look at what's even weirder than that. There's a probability that the electron will exist at some arbitrary distance away from the nucleus. That means that if I have an atom here, there's actually a chance that the electron around this atom is not here, but over, like at the end of the solar system or around another star, because this does not actually go to 0, because if you look at this, e to the r, if I put r as a really, really big number far away from the nucleus, that just makes this 1 over a big number. It just makes the probability really small, but it never gets to 0. So there's a non-zero chance that the electron around my finger here is actually around, Alpha Centauri somewhere really far away, but it's a very, very small probability. So from the top, this is a wave function. This is derived from the Schrodinger equation in quantum mechanics. But when you square it, you have to square it, and then you add up the square of the wave function to figure out the probability of finding anything. When you square it, it's just a constant times e to the minus r. And what that means is as you get close to the nucleus, the square of the wave function gets really big, and when you go far away of the nucleus, you get the square of the function getting really small. And when you integrate it, when you look really small to the nucleus, you multiply this the square of the wave function times the tiny shell. The reason it drops close to zero, the probability of finding an electron drops so low here, is because even though the kind of like the square of the wave function is high near the nucleus, you're integrating over a very increasingly small volume. Because right around the protons of the nucleus, the shell, the fractional volume that you're looking for that electron there is getting close to zero, and it drives the actual probability of finding it very, very close to zero here. And then, of course, when you get far away, the wave function squared itself gets small, so you have a low probability here, and in between you have the maximal probability called the Bohr radius. But that doesn't mean that the electron is always around the Bohr radius and everywhere else is empty. It means that the electron exists as a wave, smeared out in the entire vicinity of the atom and actually extending all across the universe. So the really crazy thing to take away from this is that the probability in the wave function of all electrons extend all throughout space. Notice that it never gets to zero. Even if I put a really big distance away, like a light year in, the wave function never goes to zero. So you can really think of electrons existing with some tiny probability anywhere in the universe, according to this theory, which could be wrong, but it yields very accurate results. So why does this myth about empty space inside of atoms persist? So it's surprising because most people encounter the concept of orbitals in high school chemistry. But in my opinion, it's mostly due to the persistence of old classical images of atoms, things we learned when we were young. The survival of this myth is a testament to how deeply ingrained classical thinking can be when in fact our world really is governed by quantum mechanics. The main idea is that electrons are not balls. You have to throw it out the window. I know it feels weird, but they're wave-like structures that we don't have direct interaction with, but that we know through experiments behave this way, like the double slit experiment and other experiments in quantum mechanics. So as we just drew on the board, the electron existing around a hydrogen atom, you can think of it almost like a fog of potential electron positions, constantly changing and fluctuating due to the electron's wave-like nature. The concept of empty space simply doesn't apply here because the electron's presence is smeared out over the entire atomic volume. And as I mentioned before, another way to think about this is to think about the wave function being the density or the most likely places where the electron could be found when we try to measure it. So the electron's wave function ensures that its presence is felt throughout the atom. The continuous presence means that there's really no empty space, just varying densities of electron probability of where it would be when we actually try to measure it. And the highest probability being at that Bohr radius for that first energy level. But as you go up in energy levels for more and more complicated atoms, then of course the distance where those electrons will be in the different orbitals would be at different distances, and also the shape and the envelope of the probable locations is different as we go up in energy level around the atoms. This way of looking at an electron as a density, it really changes how we think about chemical reactions and bonding and so on. The electron cloud model explains why atoms bond the way that they do, why they have specific shapes, and how they interact with light and other forms of energy. And I'll just give you one example of that. In chemistry, you learn about the single bond, you learn about the double bond, you learn about the triple bond, right? And the triple bond is stronger, and the double bond is in the middle, and the single bond is not as strong. Well, we learn in chemistry that these bonds come about from the overlapping nature of these electron clouds between atoms. So the single bond involves just some overlapping, and the double bond involves overlapping of multiple orbitals, and the triple bond is even more. And so the bond that atoms feel between each other is from the overlapping of these electron clouds between one atom getting close to another. Quantum mechanics governs these behaviors, and it tells us that particles like electrons really exist as what we call a superposition of states until they're measured. This superposition is what gives rise to the wave-like nature of electrons in the first place, making them spread out in space rather than being confined to a single point. And I'll give you one analogy to cover this thing called superposition of states. In quantum mechanics, you learn that a particle, like an electron, can exist in more than one state at the same time. It's called a superposition. So you might have if you think of a coin, this is a coin here. There's a heads to it, and there's a tail. So if you think of one state of the coin being heads up, and one state, a different state of the coin being tails up, then those are the two states of this coin. Now, I can tell you that this coin is in the heads up state right now, and I can tell you that when I flip it over, it's in the tails up state right now. Those are the different states. That's everyday experience. But in the quantum realm, what we find when we write these wave functions down is that the state of a quantum coin could exist in both of these states at the same time with different probabilities. So it's not like one or the other, it's just a smeared out effect like the electron, where we can say that this coin has a certain percentage of being in the up state and a certain percentage of being in a down state, but it's not that it's like flipping back and forth between the different states. It really does exist at the same time in both states. And that is very hard for any of us to visualize. So I'll give you an analogy. It's just an analogy. Here, the coin is in the up state with the heads up. Here, it's in the tails up state. But if I flip the coin while it's in the air, when I'm not interacting with it, I cannot see what's happening here because I'm not interacting with it. It's smeared out. We can say as it's flipping around that this coin is existing in the heads up and the tails up state at the same time. Now you might look at me and say, well, that's not true. It's flipping. Here it's heads and tails and heads and tails. And so, of course, if I look closely enough, I will see that it's just switching back and forth between these states. And I'm telling you that this is just an analogy. It's not a bulletproof analogy, but it's just an analogy to get you to understand that quantum states for real quantum objects really do exist in multiple different states at the same time, much like you could say that this coin is sort of existing in a superposition of these two states at the same time while it's in the air. Now, as I catch it, I've interacted with it, and I measure its location, and I see that it's heads. But that doesn't mean it was heads the whole time. It just means when I measured it, it collapsed down to the head state. But if I do it 1,000 times, I'm going to find out that about half of the time is heads and about half of the time is tails. That's the best analogy I know for superposition of states. So the next time someone tells you that atoms are mostly empty space, you can confidently explain that this just is not the case. Atoms are filled with electron clouds, and these clouds are everywhere in the atom, leaving no room for what we actually call empty space. The electron's wave-like nature ensures that it occupies the entire atomic volume, creating a rich and complex structure at the heart of matter. So, in conclusion, the notion that atoms are mostly comprised of just empty space, you could somehow shrink it down, it's really a misconception rooted in outdated classical physics thinking. Modern quantum mechanics reveals a much more intricate and I actually think fascinating way to think about it, one that doesn't seem to obey common sense. Atoms are full of electron clouds of probability that occupy the entire space with a varying electron probability density. This understanding is essential for grasping the true nature of the universe. So I'd really like to thank you for hanging out with me today on this deep dive into the realm of quantum mechanics and atoms. So until next time, keep questioning, keep exploring, and remember that the universe is much more mysterious and wonderful than any of us can really imagine. This is Jason signing off, and until next time, please stay curious. Learn anything at mathandscience.com.